Today we're going to talk about hypothesis testing. So this is definitely one of the key topics in this course. So we're kind of turning a corner here as we talk about hypothesis testing. What I decided to do is to go ahead and bring up an example. We're going to kind of break this example down and figure out how we can get to testing this hypothesis. Let me read it, and then I'll give you kind of an outline of what we're going to do. So number one, it says, a magazine claims that 75% of all teenagers have their own phones. This is the hypothesis. This is what we want to test. So we've got some claim here. We want to see if it's true. So we go out and gather data, or the researcher does. A researcher wished to test the claim and selected a sample of 60 teenagers, 54 of whom had cell phones. At the 0.01 significance level, we need to talk about what that means, should the claim be rejected? Well, what we're really trying to determine is if 75% is accurate. We got 54 out of 60. So if we think about what we came up with, 54 out of 60, let's see, so 54 out of 60, if we do that division, we get 90%. Okay, so it looks like we got significantly higher than 75. Did you catch that phrase that I used? I didn't say that it looks like it's higher or different. I said it looks like it's significantly higher. Significantly, if I can spell it. Significantly higher. I don't expect, although I guess it's possible, to go out and do my survey and get exactly 75%. There's always going to be an element of chance, right? I'm not going to get exactly 75%, even if this magazine claim is accurate. I expect to get something different. The test is to see if my 90% is significantly different. I only interviewed 60 people. I'll bet this magazine and their research interviewed a lot more than 60 people. So we're going to incorporate that into the claim. But here's what we look at. We've got this claim. We see that 90% is bigger. We want to know if it's significantly bigger. This is where the significance level comes into play. So is it significantly different? If it is, I've got this 0.01 significance level. I only want a 1% chance of making an error, of saying it's higher when it really isn't. So of saying it's higher. But I'm going to claim it's significantly higher. So say my conclusion is that, yeah, it is significantly higher. I could still be wrong, right? Well, I only want to leave a 1% chance that I am wrong. Okay, that I'm saying it's higher, but I'm wrong. Okay, so maybe I happen to walk into the AT&T store and I interviewed students there as opposed to interviewing a more random group. So there's lots of reasons why it could have been wrong, even though I say that my 90% is significant. Okay, so there's a lot of mathematics here. What's going to be really nice once we get through all of the little details here is it's going to be pretty routine as we go through and do our testing. Here's what we're going to do to set up the mathematics, because what is significantly higher? Well, we have to establish that. We're going to use the normal curve. So I would expect, if this claim is true, 75%, that most of the surveys that we do are going to lie right around 70%. We'll get some that are maybe 81 or 76. Maybe we'll get one down here that's 73.8 or 74.9. But I would expect that most of the surveys that we do fall right here in the middle, clustered around 75%. If I am significantly higher, I would expect that my 90% is down, or I should say up, is up here. Not clustered around the middle here, where I expect to be just a little bit off if 75% is correct. But if I am claiming 90% is significantly higher, I want to be away from the 75%. So what I want it to do is to land in what we call the tail. Remember that the area under the curve is 100%. The area in my tail is that significance level. It's 1%. So I'm going to leave only 1% of the 100% area where my 90% falls in. Okay, so that's the idea. So the idea is to try and prove that something isn't just higher or different, but significantly higher or different. What I want to do before we actually start doing some tests is to look at some other examples and start working on the hypotheses. As we do the hypothesis, we're always going to have a null hypothesis, which we call H sub 0, and an alternative hypothesis, which we call H sub 1 or H sub A. I don't care which language you use. I like H sub A, but it doesn't matter which one you use. So we're going to see a null hypothesis and an alternative hypothesis. I want to label just a few more things. Let's see. So I've got the tail, so I labeled that. So the tail, we call this our significance region. Or our rejection region. And you'll see how this all fits in. Over here is our fail to reject region. This is our like close enough region. So this is our fail to reject. That 1% is the significance level. We use alpha for the significance level. So the significance level for our example is 0.01 or 1%. That 1% in this case, or alpha, is the probability of committing a type 1 error. In this case, I claimed it significantly higher, even though it really isn't. I didn't have a good sample, or whatever the case might be. So that's the probability of committing a type 1 error. So there are some other things floating around here, but I'm not going to bore you with those right now. What I want to do is to get into these hypotheses, setting up those two hypotheses. We're going to have two opposing hypotheses. As we set up the null hypothesis is always going to include the equals case. So now we want to turn this into something mathematical that we can analyze. So it's going to have either equals, less than or equal to, greater than or equal to, which means the alternative hypothesis will always have the opposite, or the not equals case. So it will have, and you know what, let me make a chart here. Null, alternative. In my null hypothesis, if I use equal, the alternative hypothesis has not equal. If the null hypothesis symbolically uses a less than or equal to sign, notice always the equal sign, then my alternative hypothesis is going to be greater. Because if it's not less than and it's not equal to, then it has to be greater than. Okay, and finally, that greater than or equal to symbol. So greater than or equal to symbol, I need the opposite symbol here. If it's not bigger and it's not equal, then it is less than. So as we turn our hypotheses into mathematical statements, we always pair these together. Equals or not equals, less than or equal to and greater than or equal to and less than. So a lot of information as we start hypothesis testing, but you're going to get into the swing of things pretty quickly. At least I hope that you will. Okay, we need another example so that we can keep practicing. Let's see, I want to look at number 2 next. There it is, number 2. Now, I didn't give you enough information to test these completely. I'll do that in a minute, but I really want to focus on these hypotheses since we haven't done any yet. Kim believes that more than 50% of college students have a job. She found 65% of her sample had jobs. Is the claim correct? First of all, to review what we just talked about, let's see. Kim believes that more than 50% of students have a job. So 50% is here. She thinks that it's not going to be close to 50, but significantly more than 50. So this puts us into a right tail, just like we were up above. She found that 65% of her sample had jobs. So 65%, we want to know if it lands in the close enough to 50 region or the significantly greater than 50 region. I didn't give you enough information to do the test, so instead we're going to look at the hypotheses. So I go ahead and start with the claim. The claim is 50%. More than 50%. So I use the 50%, not what she found from her sample. That's what I'm using to test it. I'm always going to use what we're establishing in the initial claim. So for the null hypothesis and the alternative hypothesis, I go ahead and take this statement and decide where it goes. This says more than 50%. So that would be more than 50%. So the percentage is more than 50%. If I go ahead and grab that chart that I just put together, move it down here, that chart that I just put together, the more than symbol is right here in an alternative hypothesis. So as I put my hypotheses together, this becomes the alternative hypothesis. So I automatically use less than or equal in the null hypothesis. So let me put my two hypotheses together. More than 50%, that has to go here. More than 50%, or you could say 0.5. If I have more than, which automatically goes in the alternative hypothesis, less than or equal goes in the null hypothesis. Less than or equal to 50%. So having those paired off makes things a lot simpler. You don't have to think through which one's which. So I've got my two hypotheses. I don't use 65% at all. That's what I use if I were going to actually test this. This is the number that she found in her sample. So I go ahead and take the claim, more than 50%. I'm going to go ahead and label the claim here. That will help later on. Okay, let's do another one. Number 3. Let me move this up. Okay, so number 3, it says, there we go. A recent national survey found that the mean college debt after 2 years of college, so this is the mean, so we're looking at mu, is $6,423. A study of WVC grads, this is the sample now, this is what we're using to test the claim, found the mean debt to be $57.82. Does this prove that the mean differs? So now the claim doesn't say, is it significantly higher or lower than the 64.23? We just want to know if it differs. So we ignore that sample result. We just want to know if it's different. So in that normal curve, I take that recent national survey mean, which is 64.23. It's either going to be close enough to 64.23, or I want to know if it's different. There's two ways it can be different. It could be lower, like what we got in our sample, significantly lower, or it could be higher. Our sample didn't have one that was higher, but differs just means that it could be either higher or lower. Differs really means not equals. So we're looking at mu not equal to, and I always use those parameters, those population symbols in my hypotheses. So mu, is it different? So mu is not equal to, so it differs from the 64.23. If I look at my chart, I have a not equals. So I look up at my chart, and not equals goes in the alternative hypothesis, equals goes in the null hypothesis. So I'm going to put that all together. So I have my null hypothesis, my alternative hypothesis. The not equal goes in the alternative based on my chart. Always the not equals, strictly less than, strictly greater than are alternative. So mu is not equal to 64.23. Null hypothesis has to be equals then. I don't even think that through. 64.23. Notice for my hypotheses, I'm not using anything from the sample. We will when we do some tests here in a minute. But just to set up the hypotheses, I always just put numbers from that claim, like a national survey or something we're comparing it to. Okay, so that's number 3. Number 4. Okay, so in number 4, it says Joanna thinks that less than 30% of high school students consume coffee on a regular basis. Let me move this up. she found that 27% of the students she surveyed consumed coffee regularly. Okay, we don't want this for our hypotheses. That's the survey. That's the sample that she collected. We're going to use that 30% for our survey. And she thinks that less than 30%. Is her claim correct? Okay, less than 30% is, let's see, these are percentages. So P is less than 30% or 0.30. I look up at my chart. These all just happen to be alternative hypotheses, but it could be a null. But this one is the less than, which is right here. So that falls into my alternative. So automatically the null hypothesis is the opposite symbol, which is greater than or equal to. So this will be my alternative. This will be my null hypothesis. Okay, so here we go. So the null hypothesis is, these are percentages. So my percentage, looking up at my chart, is greater than or equal to 0.3. My alternative is significantly less than 0.3. Those are the hypotheses. Let me put together that curve. 0.3 is here. So if 0.3 is the true percentage, I would expect most surveys to be in and around 0.3. But we're trying to prove that our percentage of 27 is significantly less. So significantly less, think of this as an arrow. Significantly less means it's going to land over here. So that gives me a tail on the left. So this is a left tail test. The one we had up above, the tail fell on the right over here, and so that was a right tail test. So this is a left tail test with that tail to the right. Let's see, in number 3, this was number 3. Number 3 looked like this. This one is a two-tail test because we just wanted to know if it was different. Different could be significantly less or significantly more. So that's a two-tail test. And then up above we had a right tail test. Okay, so as you're looking at your hypotheses, you really want to think about that chart. Anything that involves the equal sign goes in the null hypothesis. Anything that does not involve the equals, so not equals, greater than, less than, goes in the alternative hypothesis. Be really careful of these two because this one could be, let's see, less than or equal to. This could also be like at most, because at most means less than or up to and including. So this could be at most. The other one that gets tricky with this greater than or equal to, if this one's at most, can you think of what that one would be? This one you'll see at least. So that one would be at least. Okay, so a lot of information, but we've only done up to this point the very first step of the hypothesis tests. As we're moving now into a hypothesis test, I want to show you what resources you'll have available to you. First of all, you'll have your calculator, and we're going to use those a lot for these. What I'm looking at here is the figures and formulas document, or you might have the laminated card in your textbook if you're lucky enough to get one with your book. You'll have this on the exam, on the final exam. You can use this, and I encourage you to use this. So what you'll be doing is you'll just be following these steps along. We have two different types of tests. Lots of different things we'll be testing, but two different basic types of tests. One's the traditional method, one's the p-value method. What we've done so far is step 1. State the hypotheses and identify the claim. And notice this other method here, same thing. State the hypotheses and identify the claim. So let's go on to the other one. We're going to find the critical value. That's what cuts off that tail of significance. We're going to compute the test value. Here, this means we're going to see where that sample number falls. Make the decision to either reject or fail to reject. So that means that we decide if it's significant enough. And then finally summarize the results. Well, what does that mean in the context of the problem? Okay, you'll have this with you as you're doing hypothesis testing, and I encourage you to have that with you. Okay, let's do a hypothesis test, start to finish. Okay, so is this the one I want to do? Yes. Okay, so a real estate agent believes that the average closing cost of purchasing a new home is $6,500 over the purchase price. She selects 40 new homes. So what I'm looking at right now is the sample. I'm going to put that in parentheses so that you can separate those. So this is the sample information. Okay, so sample, which does not go into our hypothesis. The standard deviation of the population is 120. Test her belief at alpha equals 0.05. Okay, what was her belief? She believes that the average closing cost is. Do you remember how to translate your mathematical symbols? Is. It's a really nice one to translate. That one just translates to equals. So I'm looking at that claim, that belief in this case, and this one turns out to be is. Let me take autofocus off. This one turns out to be is. So as I put my hypotheses together, that equal sign goes in the null hypothesis. And these are average, so that's going to be my mu. So this says that the average is or equals $6,500. Well, it either is or it isn't. So the alternative hypothesis is not equal to $6,500. I like to draw that normal curve in next. So this would be 100% of any survey results or sample results. We would expect $6,500 to be in the middle if the claim, which is here in this case, is correct. We would expect most of the sample results that people did to be right around $6,500. But she just wants to know if it is or it isn't. So these could end up to be significantly less than $6,500 or significantly more than $6,500. So we are looking at a two-tail test. Okay, so that's our first step. As I look at the procedure table, I'm going to put it over the top here for just a second. You'll see me deviate from the procedure table just a tiny bit. Sometimes I change the order. But you'll see me deviate because what I really do is I let the calculator do the computations for me, and then I summarize everything together on my paper. So we state the hypothesis, we did that, identified the claim. Step 2 is to find the critical value from the appropriate table in Appendix C. I'm not a big table person. I can use my calculator. So instead of using this, which I could do, I'm going to go ahead and use my calculator. But I will show you how to do that because it's not a bad way. I don't use Appendix C, though, because I think that's too complicated. There's a much, much nicer way to do that. We're going to use Table F. So step number 2, we're looking for the critical values. And then I'll do it this way first, then we'll do it with the calculator. And you can use any combination. The critical values, that's these guys right here. I want to know what cuts off the significance regions. So we're going to look to see what cuts off the significance regions. Let's see. So now I need that 5%. So my significance level is 5%. It's split into 2 regions. So that means we have 2.5% in both regions. So this area is 2.5%, that area is 2.5%. You don't need to think too hard because your table will do it for you. We've used this already for confidence intervals. I know you can't read it, so I'll read it for you. So two-tail test, 0.05. I go all the way to the bottom. We had 40 in our sample, so I don't need any degrees of freedom. And it says that my z-score, this is two tails, so I have a positive and a negative one, is 1.96. So 1.96. I'm looking at a z-score, though. So when I put this together, let me redraw. I'm going to put the 6,500 down here. This is my mean, or so I look at sample means. So that's my sample mean. And as I convert those to z-scores, the z-score for a mean is 0. The z-score from table F, which is so nice, is 1.96. Let's see, less than 0, so that one's negative. More than 0, so that one's positive. So that's step number 2. So that means what I really need, because I've got that 6,600 and we wanted to know if it's different. So in this case, if it's significantly more. Well, all I need is the z-score, because I don't know where 6,600 lies, if it's over here or if 6,600 is over here. So I just need the z-score for 6,600. So step number 3, I'm going to look up the test value. I'm going to compute the test value. That's just the z-score for my sample result. And my sample result was 6,600. So I'm going to do the z-score. This was for a sample, though, so I do have to adjust for my sample size, which was 40. And I have a standard deviation of my sample, so I'll call that S. Oh, no, it says of the population, so I'll call that sigma of 120. And I go to my handy-dandy formula sheet. We are in Chapter 8. I'm doing a z-test because I'm comparing z-scores. And here's how I compute the z. So x bar minus mu divided by standard deviation divided by the square root of n. So I'm just right off of my formula card there. So my z-score is 6,600 minus 6,500, x bar minus mu. This is right off of my formula sheet, divided by, you should use parentheses here, your standard deviation divided by the square root of 40. I'm going to put this into my calculator all in one step, so I need parentheses where I've put those parentheses there. If you want, you can just do 100 for your numerator, which would be fine. So I'll do it the long way, though. 6,600 minus 6,500 divided by parentheses, so this is all in the denominator. I can zoom in a little bit. I want you to see what I've got here. Divided by 120 divided by the square root of 40. Really easy to mess up if you're not using parentheses. So be really careful. You want this whole thing in your denominator, so it needs to be in parentheses. And I'll hit enter. So I get 5.27. That's a big z-score. 3 is a big z-score. So I get 5.27. So this is about 5.27. We said, based on 2.5% here and 2.5% there, that I was significant at z-scores starting at 1.96. My z-score is way the heck over here at 5.27. So I land well within my rejection region. So here's 6,600. So I called that the rejection region, which means we're rejecting the null hypothesis. This is where it's significantly different. In this case, significantly higher. So I'm landing in that significance region. Okay, so if we finish this one off, now we can go ahead and state our conclusion. So our conclusion says, so you need a piece of paper. So what we just found was that we are going to, this is fail, this is not significant, so fail to reject the null hypothesis. We didn't land there though. We landed in reject the null hypothesis, where it's significantly different. In the middle here, it's not significantly different. Out on the ends, it is significantly different. If you can remember that, it will get you through every single hypothesis test. Not significantly different is in the middle, so in and around your claimed value. And significantly different, and it could be higher and lower or just one or the other, falls into your tails. Okay, number 4. For number 4, we only have one of 2 answers for number 4. This is our decision. We're either going to fail to reject, which we don't in this case, or reject. You have a 50-50 shot. If you got everything else wrong in the whole entire hypothesis test, you can at least guess down here. So here, we're going to reject the null hypothesis. That's all. That's number 4. It's called the decision. Number 5. So number 5 is the summary. So number 5 is the most important part. You can do all of this if you've done some practice and you've learned the procedure, but number 5 really is, do you get what you just did? Okay, well, what did we just do? We started out with this claim of 6,500. The question was, were we close enough with that 6,600, or were we significantly different? guess what? We were significantly different. That's a huge z-score we found, 5.27. So our conclusion is that 6600 is significantly different. What was her claim? Let's see. Her claim, test her belief. Is she right? No, she's not right. We found that it's significantly different. So this is where you're going to convince me that you understand that. Her belief was not correct. We found the average, and you're going to use words in the context of the problem. We found that the average closing costs, you can say significantly greater, but really the language of this problem was different. We found that the average closing costs was, significantly different than 6,500. Okay, so let me reinforce it again. You could get 1 through 4 right. You could get everything correct. If you don't convince me in number 5 that you understand what you just did, it doesn't matter. I'm going to give you very, very few points because computation is, maybe 10% of statistics. It's really that conclusion and that analysis. So this step number 5 is really, really critical. Okay, let's look at another example. Let's see, let's do this one. Okay, so here's the next example. Oh, you know what? I said I would do this one on the calculator, didn't I? Let me do this one on the calculator. Okay, so on the calculator, I'm going to go to, and I brought 2 calculators because on these 84s and 83s, there are 2 slightly different functions that have you go through the different statistical prompts. So I'll show you, this is one. This is my personal calculator. Then I'll show you the other one. You might be one or the other. So what I want to do is to go into stat. I'm going to go into tests. We just did a z-test. I wish you could read this whole thing, but you can't. But if you go down here, here are the proportion tests. 2 sample tests, we just have a single sample. So it has to be that first test. So we're going to do the z-test. And then it says, what's your input data? I don't actually have all of the raw data. I just have my average of 6,600. So I leave it in stats. And it says, what is mu naught? Mu naught is this guy. That's the number that you put in the hypothesis. So that's 6,500. So 6,500. Standard deviation is 120. And as long as you have a big sample size, 30 or greater, even if it was a sample standard deviation, you could throw that into sigma as well. X bar, you know what that is? So we already have mu. X bar is the sample percentage. That was that 6,600. We wanted to see if that was significant or not. Let's see, how many did we survey? 40. And here's where you choose the alternative hypothesis. Our alternative hypothesis was not equal. Not equal is first, so I do leave it on not equal. If you were to choose another one, you'd arrow over and hit enter. Arrow back and hit enter because I want not equal. I don't do draw. Draw will draw the normal curve. I want to calculate, so I go ahead and choose calculate. And it just confirms for you. Okay, it says, okay, this was your null hypothesis. Yes, that was my null hypothesis. There's that z-score. We got it right on, 5.27. This is the p-value. That p-value is actually a teeny tiny number. I'm going to explain what that is here in just a second. And then it also just confirms that your sample average was 6,600, and it was, and n was equal to 40. So let me talk about that p-value. That 5.27, that was correct. We're doing a traditional method. With that traditional method, notice it doesn't give you the critical value. So I do need table F, and I need to have found that 1.96. And then I would say, oh yeah, 5.27 is bigger. So I do need that step. With that p-value, though, let me take this off of here. That p-value tells us what area 5.27 cut off. 5.27 starts right here. So 5.27 cut off this area right here. That's not a great picture, is it? If I redraw, normal curve, 6,500, which is right here. I'll go ahead and just let that be 0. That was my 6,500 though, z-score of 0. I cut it off way over here at 5.27. That p-value measures what this area is. That p-value was, where'd it go? 1.36, 1.36 e, which is times 10 to the negative 7. That means that I have 7 decimal places before I get to this decimal point. So the area right here, out of, remember, 100% is, or 1, since I'm changing it into a decimal, is 0.123456136. That's the area in that curve. P is also the probability of a type 1 error if we reject. So if I didn't start with a significance level, that 0.05 is really random. So if I didn't start, if someone didn't hand that to me, instead I can say, you know what, if we do cut this off at that 5.27, which was for the 6,600, it leaves me with a little teeny tiny area. That's just this size right here, 1.36 times 10 to the negative 7. So I'm only going to reject this percentage of the time. I'm only going to reject 0.0000136 out of that whole area. So that becomes the probability of a type 1 error. So is it significant? Oh yeah, because it cuts off just a teeny tiny tail. I've really exaggerated that here. Let me redo this really quickly with the other calculator so that you see both of the keystrokes. So on the other calculator, let me zoom in. This is the same TI-84. For some reason, when they came out with different versions of the calculator, even though it looks exactly the same, they just changed the input. So again, I go to the Stat menu. Let me make this darker. So I go to the Stat menu. I arrow over to Calc, just like we did. Oh, arrow over to Test, just like we did. I pick that Z-test. Everything is the same until, oh, I guess this all looks the same. Yes, this all looks the same. So then I go ahead and input my data. So this is the same. Let's see. So I want stats. This was 6,500. This was 120. X bar was 6,600 and was 40. Not equal, and I'm going to calculate that. And for that z-test, it gives me the same answers. It looks just slightly different. It gives me a title here. One thing that is different on this calculator, and many of you have already figured this out, if I go to stat and I do one variable stats, oops, stat, calc, one variable stats, this other one, you know how that heading was different for the z-test? The heading's right here. It looks like this. So I just type in what my list is. The frequency I can leave blank, or I can put a list there, and then I just go to calculate. So it's just a little bit different. Okay, let's see, that was that one. Oh, we're doing great. Let's just do one more. Maybe 2. Let's do 2 more. Let's do this next one with the calculator. We'll spend more time analyzing, less time computing stuff by hand. Okay, so at a certain university, the mean income of parents of freshmen is reported to be, this sounds like a hypothesis, right? Reported to be 91,600. Where's my yellow pen? The president of another university feels that the parent's income for her freshman is greater than, she thinks it's greater than 91,600. She surveys, okay, so all of this from here to here, this is all the sample stuff. So this stuff here is our hypothesis. Greater than, so that is mu. So the actual average income is greater than 91,600. Do you know which one this falls into? There's no equals there. So that means that one falls into an alternative hypothesis. So as I put my hypotheses together, okay, so first step, my hypotheses are the one that's in the statement here, greater than, so greater than 91,600. This is the claim. And mu, if it's not greater than, it's less than or equal to 91,600. So I'm using that 91,600, and I'm going to put 0 here. And then underneath that, that's the 91,600 because we're assuming that's mu. We think it's greater. So if it's greater, remember I said think of that as an arrow. I'm looking for significantly greater, which puts my tail over here. This points to the tail. So that's pointing to the right. So I'm looking at a tail on the right. I have an alpha again of 0.05. So my significance level, the area in the tail, just to review here, which is the probability of a type 1 error, saying it's significantly bigger when it really isn't, type 1 error, is 0.05. 0.05, remember the entire area is 1, so 0.05 or 5%. What we want to do is we want to find out what this z-score is right here. So we want to figure out what that z-score is that cuts off the significance area, or the rejection area. This would be fail to reject, the null hypothesis. And over here, that would be reject. If we land in that significance region, that would be reject. Okay, so that's step number 1. I did more. Actually, this right here is step number 1. I really like to draw that picture, though. Number 2 is the critical value. And then I'll pick up my calculator. The critical value is this number right here. What cuts off the significance region? All I need to know is how many tails I have. I have 1 tail, and I have 0.05 significance level. 100 randomly sampled people, so I don't need to use degrees of freedom, and a t. So I again go to table F, which is my all-time favorite table. I go to table F, not C. I go to table F. 1 tail now. 0.05 puts me here. And I go all the way to the bottom, which gives me a z-score. So this is where I cut off the significance region of 1.645. So 1.645. Table F. Table F gives me a critical z-score. So I'm going to start using some labeling of 1.645. 1.645. So now the question is, that 96,321, what is its z-score? I want to know if its z-score is bigger than 1.645, which makes it significantly bigger, or less than 1.645. Step number 3, I'm going to let the calculator do the work. I could do it just like I had done, but I'm going to let the calculator do the work. Okay, so here's my calculator. You can see my claim there. So turn this on. Let me zoom in just a little bit more. Okay, so I'm going to clear this. I'm going to go to Stat, Tests. I am doing a z-test. If I had a sample size that was small, I'd change that to a t-test, but I don't. It's 100. So I go ahead and hit 1. I do have stats. I don't have raw data. My null mean is 91,600. 91,600. Standard deviation for the sample was 9,555. Which I'm just reading off of the problem. You can't see. The sample mean was 96,321. The sample size was 100. And now this is asking for the alternative hypothesis, which was greater than. So the alternative hypothesis was greater than. So not equals, not less than, but greater than. So I hit enter to select that, and then calculate. Okay, so it says this is your alternative. Yes, it is. Here's our z-score, 4.94. Here's the p-value. And it's confirming your sample mean and your sample size. I got another big z-score, 4.94. So we ended up with 4.94, which was the z-score for our sample mean of 96,321. So that landed me in the rejection region. So I did number 3 this time with the calculator. So with the calculator, I found the test value, which is the z-score for 96,321 to be 4.94, which lands me in the rejection region. So step number 4, which means I'm significantly bigger. So step number 4 is to reject. I land here, so I reject. If I land here, I fail to reject. Reject the null hypothesis. That's all I say for 4. Number 5, the most critical part. Okay, so what does this mean? Well, this means that, let's see, that president was right. They felt that the parents' income for her freshman was greater. She's right. So the other president, I'm explaining now, I'm using my own words, is correct that the parents' income of her freshman, or that university's freshman, is, and I'm going to use the correct terminology here, is significantly greater than. I'm going to abbreviate. Significantly greater than that 91,600. So there's all 5 steps. Now on this one, I'm going to redo it using the P method. So what we just did is called the traditional method. And that's because we compared z-scores, the critical, and the test z-score. We can also do this using a p-value method. So if I do the p-value method, so I'm going to redo this one. Do over p-value. So if I redo this one using the p-value, I start off step number 1 with my hypotheses. I'm just looking up above and I'm going to copy them. That doesn't change. It either is significantly greater or it's less than or equal to. Step number 2, I don't need the critical value. Because what I'm doing, and I have alpha equals 0.05, what I want to do is I want to use the p-value. So here's the way I do it. I go ahead and pick up the p-value for step number 2 right off the calculator. And remember, this is the area cut off by the, in this case, the sample mean. Okay, so the p-value is 3.89 times 10 to the negative 7. It's teeny tiny, 0.1, 2, 3, 4, 5, 6, 7, until I get to that decimal place, 8, 9. Super small. That's my p-value. Okay, so I have 91, I don't even use any z-scores. I have 91,600 here. My sample mean of 96,321, it's way over here. 96,321. This area right here. So this area is my p-value, which is tiny, 3.89 times 10 to the negative 7. I have a tiny p-value. So in order to decide, well, I can look at this, right, and I can go, whoa, I'm cutting off a really, really small area under the curve that's very far away from 91,600. Just visually, I can see that this is significantly far away or significantly bigger than the 96,321. It's significantly bigger than the 91,600. But I also want to do a comparison here. I was given an alpha. That alpha is 0.05. Well, this area is this guy right here. So that's that area. My significance region cuts off an area that's greater. So this is 0.05 equals the significance region. So I cut off an area that's even smaller than my significance level. To be significant, I just had to fall into this area. And I definitely fell into that area. So I have a smaller area, so it fits inside. So that means that for step number 3, a lot of my students struggle with the p-value at first, but then end up preferring the p-value. So if I give you an option to use either the traditional, where you compare z-scores, or the p-value, they really like the p-value method. I think it's more visual. Cuts off a tiny area, and it's certainly an area inside the rejection region, inside the significance level. So for step number 3, we say reject the null hypothesis. And for step number 4, I'm just going to say C above, because I've got the same conclusion. I'm on the bottom of a paper. I'll do that. So I'm on the, so it's the same analysis, very same analysis. But that's what the p-value method does for us. Let's see. How about we'll do just one more. So I've got one more example here. This one uses a t-score. So this one says a state executive claims that the average number of acres in the state parks is less than 2,000. Oh, so less than here. Let's just jump right in. Less than 2,000. That's my alternative hypothesis. So step number 1, null alternative. Average number, so mu is less than 2,000. It could be less than or greater than or equal to 2,000. Number 2, let's see. Oh, a random sample of 5 parks. Okay, so blah, blah, blah. Let's do a p-value method here. I don't think I said, did I? So we'll do a p-value method. So that means that for step number 2, I want to know what that p-value is. So I need to enter, look, it gave me data. Didn't give me what the average was, it gave me data. And I know that I need the average and the standard deviation. So in my calculator, I'm going to enter those data values. I'm going to put them into L1. I'm going to clear this. I'm going to go to Stat, Edit. I'm going to clear and enter L1. And I'm going to enter in these acreage. 959. 1187, 493, 6249, and 541. So I just entered those into L1. I can zoom in now so you can see what I'm doing. Now that I've entered those, move that over a little bit so you can see. I'm going to quit. So I go second quit, go back into stat. Now I'm going to pick up a test. I want to do not a z-test, but a t-test. I only have 1, 2, 3, 4, 5. Definitely less than 30. So I want a t-test. I don't have statistics. I don't have something computed for me. Instead, I just have raw data. So I go over to data, and I hit enter. What is my null average? That's the 2,000. Oops, 2,000. Where's your data? It's in L1, so I already have L1 selected, or you can go ahead and hit one of your L1, L2 keys. Frequency, leave this at 1 unless you used a frequency list. This just says to use each of the acreages one time. So with frequency, leave that at 1. And my alternative hypothesis is less than. So I arrow over to less than, go to calculate. Wasn't that easy? So there's my p-value. And notice how it gave you a t-score. So it gave you a t-score. It gave me a p-value. So let me put the p-value up here. I'm going to pull this off. So my p-value, I'm not using the table F at all. I don't need a t-score or z-score, t-score for this one. My p-value is about 0.461. And remember, this is the area cut off by my average, and our average was 1885.8. I'm reading that right off of my calculator. Okay, so what does that mean? 2,000 is here from my hypothesis. 1885.8 is less than, so it's over here. 1885.8. So that tells me that the area that I've just cut off, which is this right here, so this area is 0.461. So the area that I've just cut off is 0.461. To be significant, I had to fall into an area of 0.01. So our significance level, alpha, is 0.01. Well, 0.01 is smaller than 0.461. So in this case, my significance region is here. So this right here is my significance region. My p-value is big, 0.461. Actually, it should be 0.461. This is half, right? Do you see how I'm really not giving you a good visual? What about here? Is that better? Okay, so now with that picture, does that look significant? No, because we needed to be far away from, significantly less than, and we weren't. So I needed to be in the 0.01 area, but I wasn't. I was in a huge area of 0.461. So our conclusion then is to fail to reject. So in this case, I had to fall in here to reject the null hypothesis. If I fall into this yellow area, and I don't, if I fall anywhere else, I fail to reject that null hypothesis. So anywhere else, I fail to reject. So step number 3, in this case, we fail to reject the null hypothesis. We always do everything based on the null hypothesis in statistics. It's kind of like guilty or not guilty. The verdict is never innocent. It's always guilty or not guilty. And for statistics, we do something similar. We either reject or we fail to reject the null hypothesis. Number 4, though, what's our conclusion? I'm rereading the problem. It says whether they claim that average in state parks is less than 2,000. Gosh, you know what? It's not. It's in the close enough region. It's near 2,000. So we can just say that the average acreage is not significantly less than, oops, missed a 0, not less than 2,000. Now this could have been improved by maybe, say, looking at more parks. Not a lot of parks. That certainly affects our results here. But again, if you are close to 2,000, which is in this region here, you're not significantly different, in this case less. If you're landing in a tail, then you are significantly different. I'm going to end with that. So if you are, I'm going to use what we had here, in the tail, you are significantly different. This will help you with your last step. Notice I'm using just 4 steps in the p-test. Your book uses 5, but these 4 are really what you need. Significantly different. And based on where I put my tail there, it is significantly less than. If you land here, you are not significantly different. That's just a nice general way of summarizing these hypothesis tests.